starting this session on quantum foundations. We have Marek Czachor from Polytechnic Gdansk, and also from Centre de Apostol. So let's thank Marek Czachor for his type physics and non-Diophantine arithmetic.
Mm-hmm. Yeah. Okay. So. Thank you very much for this invitation, and I think it's been 20 years since I started collaboration with Dirk Arts, and we are doing various things, and this is something related to the last period, maybe 2 years, and just recalling yesterday's discussion from the dinner, actually, I think that there was one argument which, when you hear that quantum structures should not be applicable to things which are interesting for the CLEA community, because quantum physics is applicable to microscopic systems, of course the first simplest and trivial argument that this should not be the case is that there exists something like quantum cosmology, for example. And if we are treating seriously scientists like Stephen Hawking or James Harper, for example, then the notion of the wave function of the universe is treated seriously. And if the whole universe can be described by a wave function, then any of its subsystems can be, of course, treated at least by a density matrix. So this is a trivial comment, so to say, on general applicability of quantum structures to systems which are big. But here, my intention is slightly different. Let me start with something which I call a Kant problem. There are many Kant problems, but the first one is, of course, related to the famous statement by Kant that there are ideas like space and time are given a priori, and therefore they are not influenced by the experiment. We know how it ended. So we have something which I could call a geometric Kant problem that could be rephrased in this way. Of course, Kant would not do it because Kant didn't know Lobachevsky and Bolyai because they were too young at the moment he was dying. But let me call it the geometric Kant problem. So the geometric Kant problem is that different alternative geometries are allowed by mathematics, so why does the universe obey those particular rules invented by Euclid? We know that there are different geometries, and we know what happened. So we have general relativity, we have cosmology, classical cosmology in this context, and we have predictions about the evolution of the universe, and we have disagreement. So we have theoretically a beautiful theory which predicts that the universe can be expanding, but the prediction is not it is supported by the experiment, the world that the universe is expanding, but it should not expand in the way it is observed. And the problem is with this bending of this curve, namely general relativity essentially predicts this kind of evolution, not this bending. Now this bending is observable, it's sufficiently observable to guarantee a Nobel Prize in physics. And interesting thing is that the parameter which is observed, which is the so-called cosmological constant, the observed value is something like 10 to minus 40, whereas the estimates based on the idea that the cosmological constant is related to the energy of the vacuum give roughly something like 10 to 80. So we have 120 orders of magnitudes, too small observable effect in comparison to the so-called theoretical prediction. The effect is called the cosmological constant problem, and I think it's the greatest disagreement between theoretical prediction and experiment in history of science. Right? So that's the situation for today. Now, what I'm going to tell you about is that not only we have a geometric Kant problem, but we have arithmetic Kant problem, which can be just rephrased. The previous slide could be rephrased in this way: that different alternative arithmetics are allowed by mathematics. So why does the universe obey those particular rules invented by Diophantus of Alexandria? And here, similarly to Łobachewski and Bolyai and Gauss, we have Mark Burgin, who is a Ukrainian mathematician, or Russian-Ukrainian mathematician, who now works at University of California in Los Angeles, who many years ago started to investigate this possibility that arithmetics could be also defined in a different way, not necessarily the way formalized by Diophantus. And this title of his book is very characteristic. Non-Diophantine arithmetics, or is it possible that 2 plus 2 is not equal to 4? So in one of those previous talks, I heard this Sufi proverb that 1 and 1 is 2, but we have to understand what it means and, right? So here, from this perspective, we have to understand what it means plus. And Burgin gave examples of such a situation where we have strange behavior, and it can be found in economics, psychology. For example, one of the titles of his recent papers is Synergy Arithmetics in Economics. 1 plus 1 equals 3. So this is 1 plus 1 equals 3 is typically quoted by those who investigate synergy behavior in economics, for example. And he wanted to formalize it somehow. And what he wanted to formalize also was the notion which is very popular in physics, for example, that there are numbers which are much larger than, or much smaller than. And it was Kolmogorov himself who thought that maybe natural numbers are not equal, so that there are small natural numbers, intermediate natural numbers, and huge natural numbers, and they could behave differently. It was the intuition of Kolmogorov. So there are many reasons to investigate generalized arithmetics. I want to show you one example, which is not exactly due to Burgin, but it's something which appeared in my research, so to say. When I wanted to investigate differential equations on fractals. So we have an example of a fractal, it's a Koch curve, and there is a bijection between the Koch curve and real numbers. And this bijection allows me to treat the Koch curve, which is a geometric object, as a field in the algebraic sense. So I have certain bijection, which is a field isomorphism, and I can, using this field, I can define addition, multiplication, subtraction, division of points in the Koch curve. This bijection is not a trivial one in the sense that each segment, each part of this curve has infinite length. Right? So it's not a trivial, it's not just bending the real line. It's more complicated. But here we have the formula which defines this addition in the Koch curve. It's very simple. You just take 2 points which represent numbers, you move them to a real line, then add them in the real line, and the result is moved back to the Koch curve, and this is how you add things. It's useful because before I show you that it's useful, first of all, this kind of arithmetic satisfies all the rules of arithmetic. So it's associative, commutative, distributive. You have a zero element, uniquely defined zero element. You have the one element, which is a neutral element of multiplication, and so on. And they satisfy all the standard rules. But since we have it, since we know how to add, subtract, divide, multiply, we know how to define a derivative, for example. If we know how to define the derivative, we know how to define the integral, and we know how to define the whole calculus, essentially. And therefore, we can easily formulate differential equations on such curves, and this is an example of a wave which satisfies a wave equation. It propagates along the Koch curve, and it's very easy mathematically, and paradoxically, mathematicians don't like this solution very much because it's too easy. They wanted to find something more difficult, but this was so easy that they felt offended by simplicity of the solution, so to say. Another example, very simple, which I like very much. So, if we have this bijection between our set of interest and real numbers, then this can be any bijection. So let's say the simplest thing, like x to the third. It defines new addition, multiplication, and so on. Multiplication is unchanged, as you can see, but addition is changed. This is how we add numbers with respect to the new arithmetic. We can, therefore, first of all, check all these properties which they hold. So it's just a standard arithmetic. So this f of x is again the field isomorphism from the point of view of the algebra. But we can define a derivative, for example. Now the derivative is interesting because you can try to solve the exponential equation, differential equation. And this is the solution. Right? So this is a derivative, and this derivative satisfies all the rules of derivation, like Leibniz rule, linearity, but of course Leibniz rule with respect to appropriate multiplication, which is this multiplication, which is unchanged here, but linearity with respect to this addition. So you have this strange equation, which I like very much. Oh, great, Dirk. Hi. Okay, so now we have a single set, real line. Here we have bijection of R into R. So in the same set we have two different ways of adding and subtracting. And which of them is natural, simpler, physical, given a priori, and so on? If we write it this way, no, this way. If you write it this way, it seems that this is just a standard Diophantine addition and subtraction, and this is non-Diophantine. But since this function is a bijection, we can invert it in terms of this root, and we have this formula. Now, this looks Diophantine, and this looks non-Diophantine because of these formulas. And which of them is Diophantine and which is non-Diophantine? We don't know. And we have no criterion, essentially, which could tell us what to do. So perhaps it's irrelevant. If all mathematical operations performed by us and by the nature involve the same type of arithmetic and calculus, we may be unable to tell if we have some non-trivial f or we don't have this non-trivial f, right? So, but what happens if there is a mismatch? For example, nature employs different arithmetic than we employ. Can we observe this mismatch somehow? And are there any examples of such a mismatch in any field of natural science? And the surprising answer is yes. We have such a mismatch. And moreover, we experience it in our everyday life, although we are typically unaware of it. As unaware as we were unaware of curvature of space before the advent of general relativity. We are feeling gravitational force, but we didn't know that it's manifestation of curvature. So here I claim that we have a similar experience in our everyday life, and we are unaware of it. And this is called Weber-Fechner law, which was discovered, as you can see, many years ago, 19th century. Again, this is a print screen from Khan Academy, where you can find a talk about this law. And this is essentially, this is the law which is applicable to any signals which are processed by our nervous system. So vision, sound, weight, taste. What we have, essentially, what we find, and it's confirmed at various levels. So it's confirmed in psychological tests, it's confirmed in just physical measurements of neurons, in neurophysics, in neurophysiology. And what it amounts to is simply that what happens is that if we have an input signal x, and we increase this input by kx, so this increase is proportional to x, we don't experience this as x dependent. So, previous slide, what we experience is that it's something like this, that delta x divided by x is a constant, of course in set a wide range of parameters, right? So you can measure this constant, and it is measured, and of course it's different for taste, different for vision and so on, but it's measurable, and there's a huge literature on the subject. But from my point of view, you can reformulate it as an arithmetic problem. Namely, can we define a non-Diophantine subtraction such that the difference is independent of x? So we take this difference, and this number should be independent of x, and the solution is unique. And it was found by Fechner already in 1850, and it's just a logarithm. And this is why decibels correspond to a logarithmic scale, and of course all our sensations are behaving in this way. So we can define Fechnerian arithmetic if you want, and that's how it looks like. So this is psychologists are essentially interested only in subtraction for some reasons, but you can also consider addition, multiplication, and so on. And what's interesting is that even negative numbers are positive. All numbers here are positive, even the negative numbers are positive, but of course with respect to different types of arithmetic. So in one arithmetic they are positive, another arithmetic they are negative. And you can see the example. So this is minus x in this language. So minus x is 0 minus x simply. And this is a number which is of course non-negative. But you can check that minus x plus x equals this number, which is 0, as you can directly prove. So you have this example of a strange arithmetic, and you have an example of a situation where in the same set you have two different types of arithmetic. Now, an experiment, a thought experiment, Gdansk experiment, so to say. Let's see what will happen with our space-time, so 1 plus 2-dimensional space in this context, where I model real numbers by these Fechnerian numbers. So what happens is, this is an example of a light cone in this formalism. What's interesting is that if you go to a small neighborhood of this tip of the light cone, it looks like this. So if you magnify it, it looks like an ordinary light cone. But when you look from wider perspective, you see that this is it's a Lorentzian geometry, but not Minkowskian geometry, of course. And you have event horizons here because there are no negative numbers. So you can continue these numbers, these lines here, the coordinates, but not in that direction. So this is the event horizon here. So this is infinity, in fact. So we have, and it shows you in what sense we have two types of arithmetics simultaneously. There is one arithmetic in which this will be just a standard Minkowski space in 1 plus 2 dimensions, but there is also the arithmetic which is employed by this computer when it plots these functions, and this is just a standard Diophantine, so to say. So this is non-Diophantine, and this non-Diophantine language is just a Minkowski space. But there exists the other one, which is employed by Mathematica to make these plots. So we have, and another interesting thing is that here we have our space is globally Minkowskian, but with respect to the non-Diophantine arithmetic. And with respect to the Diophantine arithmetic, it's Lorentzian, locally Lorentzian. Right? So in a small neighborhood of a point, you will have something similar to the Lorentzian manifold. So we have a problem. Two types of arithmetic can coexist in the same spacetime. Which of them should be employed in mathematical formulation of equations of physics? Is it possible that we work with the wrong one? I mean, the universe is using the different one than we are using. If so, what are the observable consequences? So another example. So I have Minkowski space. Now, my set is just an interval of length L, and I have my bijection, which maps this interval into real line. So I can define my arithmetic, and in this generalized arithmetic, this is just the Minkowski space, standard Minkowski space. So I can formulate standard relativistic physics in this space. For example, I can solve Maxwell equations. So this is again global and local picture. So this is the whole universe here, right? So I take a point. This is from minus infinity in time to plus infinity in time, and this is the light cone. That's how it looks like. If you just look at the neighborhood of this point, you get a light cone, slightly deformed light cone. It's not exactly the Minkowski space, but it's a Lorentzian manifold, so it's a Lorentzian metric, so it's a deformed light cone. But if you go to the middle of this universe, so somewhere in the middle, close to the middle, then this is the light cone. So these are space-like infinities. This is minus infinity in time. This is plus infinity in time. This is the whole history of this light cone. But locally, in the neighborhood of this point, it looks like this. So again, we have a global Minkowski structure, just Minkowski, no curvature, nothing like that. And locally, it's a Lorentzian manifold. Now let's think about the following problem. Okay, so we have this non-Diophantine. We have this universe, which is just a box. From one point of view, just a box like this. And from another point of view, if I introduce my non-Diophantine arithmetic, it's just Minkowski space. So let's formulate in this Minkowski space the problem of a field produced by a static point-like charge. We can solve it. We just take Maxwell equations. And what happens is that, of course, the solution with respect to the non-Diophantine calculus looks ordinary, in the sense that you can find it in all textbooks on electrodynamics. However, when you go back to the wrong, so to say, arithmetic, the one in which the universe is a box, then it turns out that the static charge looks like a moving charge, right? And we can even plot the velocity of this. This is my velocity. For this concrete example from previous slide, this is my velocity. So, and here, this is the horizon. 0.5 minus 0.5 because L equals 1. So from minus L2 to plus L2. So these are 0.5 are just the boundary of the universe. So on the boundary of the universe, so this is the field observed from the middle of that universe of a charge which is located somewhere here in the universe. If it's located in the neighborhood of this horizon, then it moves, looks like a charge escaping from us with the velocity of light. This is static, but it looks like moving. Moreover, it looks like moving with non-trivial acceleration. Now we can return to the Friedmann equation. So let's say in our non-Diophantine world, we introduce just standard Einstein equation. We consider the Friedmann-Robertson-Walker universe. We look for the scale factor. We obtain just the standard Friedmann equation, and this is how it would look like in the standard formalism. But here, if we now look at this Friedmann solution of the Friedmann equation with respect to the wrong arithmetic, right? This arithmetic in which the world is finite. We don't know it's finite because we perceive it through our channel, so to say, of function f. But if you look in this standard arithmetic, so to say, this arithmetic that is used by Mathematica, used here to make the plot, this is what we observe. So what we observe we observe this. And actually I cheated you in my first slide. Because when I showed you the dark energy correction to this, I showed you already my plot, right? So this is not really the dark energy solution, that's just a standard solution with respect to non-Diophantine arithmetic, but they look the same, right? So this bending is the reason for this Nobel Prize in Physics from 2011. But here we see. So one of the interpretations could be, I don't claim I solved the dark energy problem. I just want to point out that it is possible, or it's not excluded at least, that what we observe as dark energy is not any sort of dark energy or dark science of any kind, because then we would have all other types of dark objects. That's why I spoke about dark physics, like dark momentum, dark angular momentum, dark whatever. It's just a manifestation of the mismatch between the arithmetic used by us and the one used by the universe. Right? So this is one. How much time do I have?
10 minutes.
10 minutes, okay. So the big question is, of course, is there any physical law that determines f? We don't know this law, but we even don't know the law which determines this logarithm of the Weber-Fechner law, which is coming from neuroscience. So there are various approaches trying to derive this logarithm from some fundamental principle, but we don't know where it comes from, essentially, in my opinion, at least from what I read in the literature. So here we also don't know, for the moment, if there is a law that determines f. Now part 2, part 2, fractals and non-Diophantine arithmetic and dark energy problem. So, example of a fractal. I showed you before the Koch curve as an example of a set where we have this non-Diophantine arithmetic. Here I have a Cantor set where I also have a one-to-one function. I construct my Cantor set in such a way that I just cut it and split, right? So this is not the standard Cantor set in the sense that I just remove the middle part, but I just cut it and split. So here I have, in the standard Cantor set, this point will be black too, because I remove the open set. Here I just cut and split because I want to have a one-to-one relation with the unit interval. Still, it's a Cantor set. It's self-similar. It has the same dimension as the standard Cantor set. Its Lebesgue measure on the interval is 0, which is important for what I'm going to say. That's how it works. So we can define arithmetic in this Cantor set, and I could produce an analogous plot of a function moving on the Cantor set. Well, okay, I didn't do it, but I could do it, right? So we can formulate wave equation. Moreover, we can formulate the Schrödinger equation if you want on this. And one interesting thing which comes out of it is that you can solve this equation. You will have solutions similar to these solutions of the wave equation. But what happens is that this Cantor set is, from the point of view of Lebesgue measure, a set of measure 0. And we know that in quantum mechanics, states are not wave functions, but wave functions up to sets of measure 0. Right? So our state vectors in quantum mechanics are equivalence classes of functions that may differ on sets of measure 0. So we can remove the Cantor set from this room. I can remove Cantor sets, and quantum mechanics will not see it because it's set of measure 0, right? But still, it will have energy, which you can compute from this formalism, and this energy will have all the properties of dark energy because it will come out from nowhere, so to say. You will not see where it comes from. Now, the standard problem of fractal analysis is to define the Fourier transform. From the point of view of quantum mechanics, is to define the momentum representation. Mathematicians generally don't know how to do it, or at least they have great problems with the simple example of the Cantor set. And this non-Diophantine approach is just trivial. So you can see, so this is just standard example of a standard Fourier transform. This is an analog of the same situation here. You have a function which maps Cantor set into Cantor set. You have Fourier transform and the reconstruction theorem. Here we have a function defined on the Sierpinski set, and you have examples of reconstruction. This is with 5 terms, I think this is with 50 or 30 terms, right? So it just works. You can define completely new symmetries, because once you know how to multiply and add and so on, you know how to rotate. So you can produce rotations. So this is a circle. This is a phase portrait of a harmonic oscillator, a classical harmonic oscillator, which oscillates in fractal in the Cantor set and in Cantorian time. But on the other hand, it's just a circle obtained by rotation. So this is a circle of one radius, then you have 10 circles of different radii, then you have 50 circles of different radii, and this has rotational symmetry. Has rotational symmetry, right? Because, of course, with respect to appropriately defined arithmetic. So it's an example of an internal rotation symmetry. That's interesting. You can do the same with hyperbolas. You know, we coined the term Ogorzelec sets, because the sets we were getting were quite similar to what Ludwika Ogorzelec was producing in her installation. So that's we called, and this is the last slide, right? There is a kind of correspondence principle. Look at this function. It's a bijection. These are plots of the same function. But here is from minus 30 to 30, and here is minus 3,000 to 3,000. Here we can see that it's not a straight line. Here you will not see it's not a straight line, because the differences are smaller than the thickness of the curve. So for numbers for which this numbers as big as those you can see here, this will be just standard Diophantine, effectively. Indistinguishable from the standard Diophantine arithmetic. But if you go here, okay. So here, at the small scales, you have difference, and you can, with this respect to this mathematics, this arithmetic, you can define a derivative, and you can define the differential equation for the exponential function. The differential equation is this: derivative of a function equals this function, and is at 0 equals 1. And this is a unique solution which you get, and this solution looks like this for this concrete f. So this is, when I saw this picture by accident, so to say, I just experimented with this kind of plot. I said, wow, it looks like expansion of the universe, not only with dark energy part, but also with the inflation part. You see? So many aspects really of dark energy, and this is the last slide, because here are just references to some works we've done, and here below you can see the references to some important papers by Mark Burgin. I recommend, for example, this one: 1 plus 1 equals 3. Right? So it's showing that this is, in some sense, it's non-Diophantine in a way. Okay, thank you very much.
Okay, we have some time for questions, comments, remarks. Yeah.
One question is, wavelets have been developed for fractal abstraction, yes. So,
Yeah. And
my question is N. I mean, and the other thing is also the fractional derivative. Fractional derivatives, the fractional calculus.
fractional,
Fractional calculus.
fractional, yes, with non-integer.
Yes.
Okay. It's completely different. So it's unrelated. In this language, you can also formulate the fractional derivatives if you want. Why not? Because if you know, because fractional derivatives are formulated mathematically in terms of integrals and derivatives. Standard integrals and standard derivatives. You have various definitions of fractional derivatives. So we can do the same, because you know how to differentiate and how to integrate. So if you wanted, you could, of course, produce it, but it's not needed. Concerning wavelet analysis, wavelets are self-similar in a certain sense, because they are constructed in such a way. Therefore, they are relatively natural for certain sets, right? But okay, here you can also have any other signal analysis. You can have, from the Cantor set, you can have wavelets, you can have Fourier transforms, and so on. With some other approach, you can try to formulate something like a wavelet for the Cantor set. You can try, but it's not really different. load. So people tried a little bit in that direction, but I don't have a feeling that they were extremely successful.
So you have a particular law in the new arithmetics that you translated back or proofs relations to one of our standard arithmetics. I was wondering, I mean, how do the new law looks like? I mean, it's some kind of parameterization, but you may say, okay, the result is due to the true nature is a non-standard arithmetics, could it be that actually is, okay, since that it's some kind of choice that we can make, I can choose nevertheless to describe that standard arithmetic is just that the law is going to look different. Am I correct in understanding that?
I'm not sure. I'm not sure that you can always find the arithmetic which will explain it. Because that's I understand.
I don't know, rather let's say that they found a particular arithmetic which predicts things such as dark energy, but at the same time they predict this in the language of, demonstrates in the language of our standard arithmetics, is going to look like a modification of a particular.
Yeah, for example, static charge looks like a moving chart.
Yes.
That's and I think that the fundamental problem is slightly different. That we can formulate. Let's say we know the laws of physics in the correct form. So, for example, we know that we have Lagrange equations, which define whatever, right? Now, so let's say we know the laws. Now the problem is that we don't know in which arithmetic they are formulated by, or in which arithmetic they are satisfied by nature. See, I can formulate Maxwell equations from a Lagrangian perspective. Okay, I take Jackson rule. I just do it, I compute it. I know the law, it's electrodynamics. But if nature is using this law but different arithmetic, there will be discrepancies between what I would expect and what nature produces. That's the point. So if nature really fulfills Einstein equation of general relativity, but with certain non-Diophantine arithmetic, then in this non-Diophantine arithmetic there will be no dark energy and there will be no accelerated expansion.
The question is if it would not be saying that if there's another law, at least it's not arithmetic.
It would satisfy the standard law, but with non-standard arithmetic.
Is the opposite true?
I don't know which is true. I don't know which is true. I simply show that such a possibility in principle exists, and we don't know. What we are looking for is essentially if there are examples in science, wherever, where we can find this kind of discrepancy. And one example is, of course, the Weber factor. Perhaps dark energy is another example, but I don't claim it. I just show that if we are looking for places where we have great disagreement in theory and experiment, then dark energy is clearly an example. Right? So maybe it's related to the choice of arithmetic, or maybe not. Well, it's just.
Any other question? Okay, I have a clarification question.
Mm-hmm.
So regarding your more philosophical perspective.
Mm-hmm.
So, as I understand in your talk, you're claiming that nature is written in mathematical terms. And
Yeah.
we're trying to
Okay.
reach the final mathematical equation that kind of discovers the true nature of
That's what
physics.
we essentially believe as physicists, right? Physicists in general believe that there is something like a physical law.
That there is the theory of everything.
For example, I don't know, there are laws, clearly, right? So that's what we believe. Now, what I claim is that we have there is a certain ambiguity which is overlooked from the very beginning, that we have this freedom in choosing arithmetic, in which we will have the same law formulated in different arithmetics will look different, simply. But it will be the same law.
And
For example, the law which states that a particle propagates along a trajectory which is which minimizes certain function. We define this functional, it's an integral from Lagrangian, etc. We know how to derive this trajectory from Lagrange equations. And the problem is that we don't know if we are performing it in the same arithmetic as nature is doing.
So arithmetic possesses its own, nature possesses its own arithmetic.
Yeah, in principle it could, as it possesses its own geometry. Right? Space, Kant, that's why I started with Kant. We said space and time are given a priori. What we typically believe is that addition and subtraction, multiplication, division of numbers is given a priori. That's what I question. That's what, not I question, Bulgin is questioning it, in the same way as Łobachewski and Bolyai questions the axiom of Euclid. So he just questions the axioms of Diophantus, simply. And here it should not be surprising that we can question assumptions where everybody is questioning assumptions of Kolmogorov about probability, right? It's not so heretical here in this place to question another axiomatic system.
Well, is there any other questions? Let's take our speaker once more.